there, A&P2 students. Welcome to Blood Vessels Part 2, Chapter 18 in your textbook. In this video, we will be discussing how blood pressure is maintained through various neural and hormonal controls, and we will be focusing on the short-term regulation of blood pressure. Maintaining a steady flow of blood throughout the body is crucial for life, and this is maintained by blood pressure. So exactly how is blood pressure maintained in an ever-changing dynamic system? Let's take a look at our favorite equation for blood flow that we talked about in great detail in our Part 1 video. And let's substitute cardiac output for flow because this is the amount of blood that flows through the system in a minute. And then we'll solve the equation for pressure, and then we can see that pressure is directly related to both cardiac output and resistance. So when we want to understand how blood pressure is controlled and maintained, we need to study how both cardiac output and peripheral resistance are controlled. The fine control involved in maintaining blood pressure requires the coordination of the heart, blood vessels, and the kidneys. The kidneys have a major influence on both blood volume and blood pressure, and we will study this system later on in the semester. For now, we'll focus on the heart and cardiac output and the blood vessels and peripheral resistance. The delicate balance that is needed to maintain pressure at a level to sustain life is a fairly complicated mechanism that includes both short and long-term regulation, and intrinsic and extrinsic controls as well. Intrinsic controls affect local blood pressure and are based on the metabolic needs of a particular organ or tissue, whereas extrinsic controls tend to have a more global effect on blood pressure. Let's focus for now on the extrinsic controls that influence blood pressure on a body-wide basis. And we'll take a look at the two types of short-term regulation, neural and hormonal control. Neural controls will alter both cardiac output and peripheral resistance. Now, altering peripheral resistance controls mean arterial pressure by altering blood vessel diameter on a moment-to-moment basis. Altering peripheral resistance can also redistribute blood to various organs that are in a higher metabolic state, such as during exercise. We've already studied two of the three neural controls that we're going to talk about here when we looked at extrinsic control of cardiac output. Now, these controls work through a negative feedback system, and the sensory receptors are located in key places within the blood vessels. And we'll look at those locations in just a bit. Now, the control centers for these reflexes are located in the medulla oblongata, and as mentioned before, two of them affect the heart and cardiac output, and one affects blood vessels directly. The three centers are the cardioacceleratory, the cardioinhibitory, and the vasomotor centers. From the cardioacceleratory center, the cardiac nerves carry the sympathetic influence to the heart, and from the cardioinhibitory, it's the vagus nerve which carries the parasympathetic. We also saw that the heart is in a state of vagal tone, which brings down the heart rate. Unless there's some physiological change, such as stress or exercise, which will help tilt the balance toward the sympathetic system, which will increase the heart rate and increase the cardiac output. Let's take a look at our equation and relate what I just said to it. So we see that cardiac output has a direct relationship to pressure. So as cardiac output increases, so would pressure. And this is controlled by the sympathetic nervous system. And the opposite is true for parasympathetic stimulation to the heart. Cardiac output would decrease, therefore decreasing pressure. And remember that at rest, the heart is in a state of vagal tone, so pressure should not be high. Now let's consider the neural control related to peripheral resistance, and this is controlled by the vasomotor center. Try not to let this busy picture confuse you. I like it because it shows the vasomotor center in the medulla and the sympathetic nerves going to the blood vessels. Blood vessels do not have parasympathetic input, and so the way it works here is that the sympathetic nerves will either be stimulated, causing vasoconstriction, or inhibited, allowing vasodilation. Here, with the blood vessels, we're tipped more toward the sympathetic nervous system. We see blood vessels being in a state of what's called vasomotor tone, which is a state of moderate constriction. And the degree of vasomotor tone will vary from organ to organ, and any shift in physiology will change that. These three cardiovascular centers in the medulla oblongata are receiving information from the pressure and chemical sensors in the vessels. These are the baroreceptors that are within the vessel walls that sense stretch. When pressure is high and blood vessel walls are on a stretch, the baroreceptors sense this and will cause vasodilation, which will decrease blood pressure. Within the same vessels that house the baroreceptors, there are also chemoreceptors that sense concentration changes in carbon dioxide, hydrogen ions, and oxygen. And these receptors can stimulate changes in both cardiac output and peripheral resistance. These receptors are working with the control centers in the medulla oblongata that was just mentioned in a negative feedback loop. And that's what these pictures are showing from your textbook. And these pictures are relating to the baroreceptors. So that covers the neural control for short-term regulation. The hormonal controls for short-term regulation will be covered in our group wiki project. But for your cardiovascular exam, please know the names of the 4 hormones and which organ produces them. As mentioned in the beginning of this video, the long-term regulation for blood pressure is going to be covered extensively when we study the kidney. So that's it for this video.